Welcome back to the lectures in chemistry on the atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry in the Indian Institute of Technology, Madras. And you have my email addresses in this page, so please feel free to contact. Now, this lecture is a tutorial lecture. This covers some of the lecture materials of the past 2 weeks on the problems and solutions related to Hermite polynomials and hydrogen atom. Like what I have done with the previous tutorials, let me give you the problem statement first and then take you through the solutions. Very often the solutions will be also not necessarily solutions, but hints or steps. Okay. Complete solution to the last detail I don't think I need to give you, because I think you should be able to do the rest of what I leave it as fairly obvious. Okay. So, let me start with the problem sets. Okay. So, this is Hermite polynomials and hydrogen atom. Okay. So, these constants are, you might use them. I think in these this particular problem set I am not probably giving any numerical problem, therefore you may not need these things, but keep this in mind. The very first problem is on Hermite polynomial. Now, these are all mathematical tools and I am hoping that some of you will actually do this mathematics fairly on your own and be able to derive simple expressions and become more comfortable with the technique. Therefore, this whole tutorial may look like it is nothing but mathematics of differential equations and simply substituting in differential equations various things or calculating integrals. But a certain amount of drudgery is really required in order for you to understand the nitty-gritty details of how to calculate things in quantum mechanics. Therefore, in quantum chemistry particularly, where you have a lot of numerical inputs that will come later if you were to become an expert quantum chemist. So, details are given here. Attention is all in the details, as they always said, and I have also said this many times, the devil is in the details. Therefore, it is important for you to go through these carefully and understand for yourself that problems of this kind are fundamental to your they are stepping stones for your more difficult problems in the research, in the area of research in various fields. First problem is on representing the Hermite polynomial through a generating function. Okay, the generating function that you see on the left hand side is an exponential minus t square plus 2tx. This is an exponential function in t and the x, and if you expand the left hand side in a power series, you would see it is a function of x as well as a function of t, and this is expanded as a power series in t raised to n by n factorial with the coefficients which are functions of x, and those coefficients turn out to be the Hermite polynomials of various orders n from 0 to infinity. So, the problem is to verify using the above, use this equality and generate the first 4 Hermite polynomials. And I have just given some words, namely for obvious reasons, the left hand side is known as generating the Hermite polynomials through a power series representation on the right hand side. That is, the coefficients of the power series are Hermite polynomials. Okay, now how do we go about? Okay, there are two ways of doing it. One is a brute force method, the other is a slightly more involved and fundamental method of Taylor series. Okay. First one, let us do the brute force method. And I will leave the steps in between. I am not going to fill up every gap. Please, if you are solving this problem, you are only getting the help to do things by yourself. E to the minus t square plus 2tx is given to you as the series h n of x, t raised to n by n factorial. Quite obviously, if we expand this as a power series, okay, it's like, you remember, exponential minus x is 1 minus x plus x squared by 2 minus x cubed by 3 factorial plus x raised to 4 by 4 factorial minus and so on. That is exactly what we will do. Therefore, this term is equal to 1, let me write that here, e to the minus t square minus 2tx. Okay. Then it is 1 minus t square minus 2tx plus t square minus 2tx divided by 2 minus t square minus 2tx square, this is cube, divided by 3 factorial plus and so on. Let us do that for the first 2 or 3 polynomials so that you know what is being done. Okay. So, now we collect this is obviously h0 of x plus h1 of x times t plus h2 of x times t squared by 2 factorial plus h3 of x times t cubed by 3 factorial plus so on. That is what is given. Therefore, right away you can write h naught of x is equal to 1. Always trivial results are the first one every teacher is happy to give, and as though he solves the problem really nicely. This is trivial. Okay. h1 of x is the coefficient of t. Okay. On this side, the coefficient of t, if you remember, if you recall, this is t square and there is no powers of t here, because when you expand this, the smallest power of t that you will have is t square, and then you will have t cube and t to the 4 and so on. So, there is only one term, namely minus of minus 2tx, which is 2x. So, this is h1. Okay. h2 of x is the coefficient of t square, and now you have the coefficient of t square from the first term, namely minus 1, and you have the coefficient of t square from here, which is the term is 4t square x square. That is what you would get. Let us do t square by 2, that is what we need, isn't it? Coefficient of t square by 2. So, if we do that, this 2 goes away. So, what we have is plus 4 x square by 2, and the expression is 4x square minus 2 divided by 2. Okay. And you can see that this 2, you don't need them, therefore, the coefficient of this term h2 of x is 4x square minus 2. h3x is the coefficient of t cube by 3 factorial, and that, if you look at here carefully, there is an a minus b whole square. So, the ab here, the 2ab term will contain a t and a t square. So, that is a t cube. So, what you have is minus 2 into 2 minus 4x divided by 2. So, minus 4x divided by 2, that is one term, and the other t cube term that you can get is this one, a minus b whole cube, this term, a minus b whole cube equivalent. So, there is a minus b cube, which will give you, and also there is a minus sign here. So, this will give you 8x cube by 3 factorial plus 8x cube by 6, which will be essentially minus 8x cube minus 12x by 6, and therefore, you can see that the coefficient is 8x cube minus 12x, and that is h3 of x. So, this is a brute force way. There is another nice way, which is a function, if it is a power series, you can see this e to the minus t square by plus 2tx. Okay. The function, if this is, treat this as a Taylor series, expand this using a Taylor series at t is equal to 0. So, if you expand any function of t as a Taylor series with around t is equal to 0 or not at around t is equal to 0, then you will have the solution f0 plus df by dt evaluated at t is equal to 0 times t plus d square f by dt square evaluated again at t is equal to 0 t square by 2 plus d cube f by dt cube at t is equal to 0 multiplied by t cube by 3 factorial and so on, because the Taylor series of any function around a point or near a point is given by the value of the function at that point and all the derivatives which we hope are analytic and continuous, whatever that is, they all exist. This is what is given. And now if you think of the exponential minus t square plus 2tx as a function of t, then when you put t is equal to 0, you will get what is left over is the function of x, and that function of x is essentially the hn of x here. This one. Okay. So this is essentially a Taylor series where hn of x is the d of this function divided by dt, whatever is the order, nth order derivative evaluated at t is equal to 0. So then it is easy for you to get exactly the same result, namely e to the minus t square plus 2tx. If you evaluate f of 0, that is 1 because the exponential of 0. Then df by dt is going to give you e to the minus t square plus 2tx times 2x minus 2t, okay, 2x minus 2t. And if you want to evaluate this at 0, then this whole function is evaluated at t is equal to 0. This becomes 1 and this becomes 2x. Therefore, the df by dt evaluated at t is equal to 0 is 2x, and that is the first term h1 of x. Now, d square f by dt square, we will take the derivative from this point, namely d by dt of this function, e to the minus t square plus 2tx times 2x minus 2t, because it is already the first derivative. And so this will give you again 2x minus 2t whole square, okay, e to the minus t square plus 2tx, and then you have the derivative of this term, which is e to the minus t square plus 2tx times minus 2. Okay. So this has to be evaluated at t is equal to 0, and you do that, evaluate at t is equal to 0, this whole function. So if you do that, you get 2x square, which is 4x square, and you get a minus 2, everything else becomes 1 or 0. Therefore, this gives you 4x square minus 2, and that is equal to h2 of x. Okay. So now you can obviously do this by taking the derivatives, successive derivatives of this function as a function of t, and if you set that t equal to 0, whatever is the coefficient that is left over is this one. So these are essentially d raised to f, d to the power, dnf, dtn evaluated at t is equal to 0. That's that. Okay. So this is the other method. As you learn more and more, you try to be more and more efficient and quick in doing. Brute force is the last thing that you do. If you know no other method, yes, go ahead. Use the brute force method. Now, let's go to the second problem. Second problem is now on Laguerre polynomials, which were provided to you as a solution to the radial part of the hydrogen atom. I have circulated in the lecture notes a fairly elaborate set of notes on the hydrogen atom, and somewhere in the middle of the lecture set of 30-35 pages, you can see the Laguerre polynomials being given. Now, we have a simple mathematical tool for calculating the Laguerre polynomials or evaluating them, and this is a generating function that I have given here for the log polynomial. But now we assume that you remember in the case of hydrogen atom, the log polynomial has two indices n and L. Here we have the log polynomial with L equal to 0, the first expression. It is again repeated derivative of a function, and use this to generate the first 3 or 4 polynomials. Why do we need that? We need that to calculate the actual hydrogen atom log polynomials that we have obtained in the earlier lecture notes, the L, N, L. In our case, N is the principal quantum number for the hydrogen atom, L is the angular momentum quantum number, and L can take a maximum value of n minus 1 and the minimum value of 0. Therefore, the log polynomials for any n, we have n log polynomials. So, if n is 1, there is 1, n is 2, there are 2, if n is 3, there are 3. That is given by this expression. So, and that uses the n plus 1 of x, which is calculated from the previous step. Again, it is purely algebraic result. Okay. Let us look at that. Problem 2. Let us first calculate the 3 or 4 Ln of x, and Ln of x is the exponential x divided by n factorial times the nth derivative with respect to x of the function x raised to n e to the minus x. So, L0 of x, the derivative is identity 1, n is 0. Therefore, this is x raised to n, n is 0. Therefore, L0 of x gives you 1. Okay. L1 of x is the first derivative, but of this function e raised to x by 1 factorial, n is 1, d by dx, and x e to the minus x, which will give you e to the x, e to the minus x, okay, times e to the minus x. So, that of course the exponential cancels out, so it is 1 minus x. L2 of x will be e raised to x divided by 2 factorial d square by dx square of the function x square e to the minus x. Okay. Therefore, you have to take the derivative, 2 derivatives. So, it is e to the x, e raised to x by 2 d by dx of 2x e raised to minus x square e raised to minus x. So, if we take this one more derivative, e raised to x by 2 into 2 e to the minus x minus 2x e raised to minus x, that is all from here, and then you have 2 terms from this one, minus plus x square e raised to minus x minus 2x e raised to minus x. So, this will give you, there is a minus 2x here, so it is minus 4x, and there is a 2, there is an x square. So, what you have is 1 by 2, exponential x and minus x cancel out, there is a 2 minus 4x plus x square. This is L2. One more derivative, L3 of x. I would leave it to you to actually get the form. Let me write down the final answer. L3 of x is given by 1 by 6, okay. 6 minus 18x plus 9x squared minus x cubed. Okay. Basically, you have to take the derivative of e raised to x by 3 factorial d cube dx cube x cube e raised to minus x. That is what you have to do. So, it is a repeated application of differentiation. Okay. Use these L1, L2 and L3 to get the next function L, n, L of x. Okay. So, if n is 1, in our case L is 0. Therefore, if we have to use the LNL expression, recall that the expression for L, n L of x is minus 1 raised to L, the nth derivative with respect to x of the function Ln plus L of x. Okay. So, if L is 0 and n is 1, then you have L1 of x. Okay. I do not even want to write L0 of x, because L0 is there is no L anyway. So, the first one for which L is can be mentioned is n equal to 1. So, that will be when L is 0, this is 1, and there is no derivative, and therefore, L1 of x 0 is L1. Okay. And L1 is what? 1 minus x, which is 1 minus x. Okay. If you do L2, then there are two functions, L2 of 0 and L2 of 1. So, you have L values equal to 0 and 1. So, let us do the case L equal to 0, which is L2 of 0. You know immediately that this is going to give you nothing other than the original L2 of x. It's also there, you can see that, because if this L is 0, this L is also 0. So, what you have is Ln 0 is the same as Ln x. Okay. Now, L2 of 1 is minus 1 d by dx of, since n is 2 and L is 1, this is L3 of x. Okay. So, L3 of x we have calculated already. Take the derivative of this, okay, and you will get minus 18 plus 18x. You will get minus 1 times minus 18 plus 18x, and then you have minus 3x squared. Okay. So, 18 plus 3x squared. So, what you have is L2 of 1 gives you 18 minus 18x plus 3x squared. The next problem is the follows. Is again on the Hermite polynomial, where now you write the Hermite polynomial using the operation of this power with the differential inside on identity 1. Okay. This will give you h and x. Again, it is only to be verified by simple application of the algebraic calculations. So, let us do that again. 2x minus d by dx raised to n acting on 1 is hn of x. Okay. So, when n is 0, of course, h0 is 1. So, let us not consider h1 of x. h1 of x is 2x minus d by dx on 1, which will give you, of course, d by dx on 1 is 0. So, it gives you 2x, and therefore, that is h1 of x. h2 of x is basically 2x minus d by dx operating on 2x minus d by dx on 1. Remember, n is 2. Therefore, when you have operators like this with the raised to power, it means essentially operating them one after the other. So, here you know that this will give you 2x from the previous result. Therefore, now you have 2x minus d by dx acting on 2x gives you 4x square minus 2, and that is equal to h2x. So, now it is quite clear what you should do for h3 and others. It is basically repeated application of this derivative, 2x minus d by dx, 2x minus d by dx, and 2x minus d by dx on 1. So, I think you have seen this, it is already 4x square minus 2. Therefore, you have 2x minus d by dx on 4x square minus 2, which gives you 8x cube 2, gives you 2x on 4x square gives you 8x cube, 2x on minus 2 gives you minus 4x, and the d by dx on minus 4x square gives you another 8x. So, that it gives you 8x cube minus 12x, and that is h3 of x. Okay. So, likewise you can carry this calculation for higher order polynomials. Problem 4. This is a fairly involved problem. I think it is important that we use spherical polar coordinates for the hydrogen atom, but now the spherical polar coordinates should be used to get the angular momentum, the orbital angular momentum operator in the case of hydrogen, obtain an expression in polar coordinates for the square of the angular momentum operator. Identify the same in the Schrodinger equation for the hydrogen atom. The second step is very important. In fact, precisely the angular term is nothing but L square by 2I, where I is the moment of inertia for the electron in the hydrogen atom. And that L square operator is what we are going to get through this problem. Okay. Now, this is somewhat long, so let's try and do this slowly. But the algebraic steps are again fairly clear if you know differentiation and integration and you have been following the lectures. So, the angular momentum is obviously given in Cartesian coordinates as the x component, angular momentum y Ly plus z Lz, and it's r cross p in the classical definition, and you can write up therefore Lx is minus IH bar when p is replaced by, you have minus IH bar d by dx, d by dy, d by dz, then Lx will be y dou by dou z minus z dou by dou y, and Ly is minus IH bar z dou by dou x minus x dou by dou z, and Lz is minus IH bar x dou by dou y minus y dou by dou x. It's easy to remember, this is cyclical. Yz, Zx, Xy, Zy, Xz, Yz, Yx. Okay. Now, you should recall from the lecture notes and also the previous lectures that the derivative dou by dou x in spherical polar coordinates is given by this expression sin theta cos phi dou by dou r plus cos theta cos phi by r dou by dou theta minus sin phi by r sin theta dou by dou phi. And likewise for the operators dou by dou y is sin theta sin phi dou by dou r plus cos theta sin phi by r dou by dou theta, partial derivative, plus cos phi by r sin theta dou by dou phi. And the last one, dou by dou z, is cos theta dou by dou r minus sin theta by r dou by dou theta. Okay. So, these are expressions which were derived and they are given in the lecture notes in accompanying this course, and we will use this to write the Lz, for example, which is minus IH bar dou by, sorry, is minus IH bar. No, let me not do Lz. Lz is slightly longer, but the final result is extremely simple. Let's do Lx. I think Lx is simpler. Minus IH bar y dou by dou z minus z dou by dou y. And remember, in polar coordinates, x is r sin theta cos phi, y is r sin theta sin phi, and z is r cos theta. Okay. That's the polar coordinate expression. Therefore, you simply have to multiply the x, y derivative terms. So, the first term is minus IH bar, okay, or sin theta sin phi, it is y dou by dou z. Sin phi times cos theta dou by dou r minus sin theta by r dou by dou theta minus y by, so the other one is z d by dy, therefore minus r cos theta times sin theta sin phi dou by dou r plus cos theta sin phi by r dou by dou theta and plus cos phi by r sin theta dou by dou theta dou by dou phi. Okay, this is what it is. You can simplify it and cancel the terms. For example, this gets cancelled, okay, and then there is also a sin square term. This is sin square theta term, or sin phi, or cancels out. So it is sin phi sin square theta, and this is sin phi cos square theta with the both with the minus sign. Therefore, they add up to give you 1. So the final result is minus IH bar minus sin phi by dou theta times minus cot theta cos phi dou by dou phi. Okay, just do this algebra. In a similar way, you can get Ly to be minus IH bar cos phi dou by dou theta minus cot theta sin phi dou by dou phi. So this is what I meant when I said Lz is very, very simple. It's minus IH bar dou by dou phi. But the cancellation of the terms will happen when you substitute Lz as x dou by dou y minus y dou by dou x. If you do that, okay, you will get this term. Okay. So this is Lx, Ly and Lz. Therefore, to do L square, you do exactly what was done in the lecture notes again. Lx square plus Ly square and Lz square as repeated application of Lx on Lx plus Ly on Ly plus Lz on Lz. And when you do that and add all these terms, which takes probably about half an hour to an hour, the answer that you get L square is minus h bar square into 1 by sin theta dou by dou theta times sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square. Okay. Now, this is not something new. This is exactly what you have as the angular part. Please remember the hydrogen atom Hamiltonian. They call that. There is a radial part and there is an angular part. The radial part is minus h bar square by 2me times 1 by r square dou by dou r of r square dou by dou r plus 1 by r square sin theta dou by dou theta sin theta dou by dou theta plus 1 by r square sin square theta dou square by dou phi square. This is all that you have, minus you had this potential energy term, that is square by 4 pi epsilon naught r. Now, identify these terms, whatever that you calculated so far. The term that you calculated, the L square, is minus h bar square this, okay, and that's minus h bar square times sin theta dou by dou theta sin theta dou by dou theta plus sin square theta 1 dou square by dou phi square. The only 1 by r square is common. In fact, the minus h bar square is also gone. So, what is left over is 2me r square. So, essentially the term hydrogen atom function contains, the Hamiltonian contains a radial r dependent part, the derivative. Well, it's okay. I mean, let's write that out. Minus h bar square by 2me r square dou by dou r square dou by dou r, and then you have minus L square by 2me r square. This is nothing but I, the moment of inertia of the electron moving around the nucleus at a radial distance of r. and then you have this potential energy Z E square by 4 pi epsilon naught R. Okay. So you see that the angular momentum is right here in the angular part of the hydrogen atom. So it's L square by minus L square by 2I. Sorry, it's not minus L square, it's plus. It's a minus h bar square, so it is plus. Okay, L square by 2I. So this is the association of the angular momentum with a hydrogen atom, and therefore you can see that the rotational part as well as the distance, the radial part of the hydrogen atom are both coupled to each other. Okay. So this is the problem number 4. Okay. Let's do one more problem before we stop at this tutorial and then continue the same tutorial as part 2 in the next half. So let's finish the next one, which is also a somewhat involved problem, I believe. Oh no, it's not involved. Okay, it says very simple. It says it verify the relations, the L square operator we just discussed, acting on the spherical harmonics YLM theta phi, which we already know as solutions, is just a verification that the YLMs are actually the eigenfunctions of the L square and the LZ operator, and give you the eigenvalues h bar square L into L plus 1 for the L square operator and h bar m for the LZ operator. Okay. Now, simple things first. LZ is the simple thing first. LZ operator on YLM theta phi. Okay. Remember, all YLM theta phi, the function, the phi dependence is only e to the IM phi. The rest of it is function of theta and some normalization constants. Some normalization constants which depend on L and M. Okay. Therefore, the LZ operator being minus IH bar dou by dou phi, the only action of this operator on YLM theta phi will be only to do this minus IH bar dou by dou phi on e to the IM phi, because the other part is theta part, not affected by this. And this gives you right away minus I into plus I in h bar m, and it gives you IM phi, and that's exactly what you have in the tutorial, h bar m YLM. This is true right away. Therefore, it's very, very elementary, and there should not be any confusion about that. What about the L square? We'll do it for a simple case. L square on say y10, because we'll again ignore the theta, the phi part, because anyway it's going to give exactly the same result if you put the phi part in. This is supposed to give the final result. Since L is 1 and M is 0, this is supposed to give h bar square, L into L plus 1 is 2, and it should give you y10 theta phi. As per this relation, L is 1, therefore L square on y10, this is not M dependent, it's h bar square into 2. Okay. Let's see, y10 is some constant times cos theta. The constant appears on both sides, so we don't need to do that. So we will simply write y10 as the cos theta. Okay. Therefore, the operator that you have to worry about is 1 by sin theta, dou by dou theta, sin theta, dou by dou theta of cos theta. That's the y10. The other term, which is 1 by sin square theta dou square by dou phi square, will not change the cos theta, it will be 0. Therefore, we don't need it. This is the only thing, and therefore, we can evaluate this immediately as 1 by sin theta, okay, dou by dou theta, and this gives you minus sin theta, so it gives you minus sin square theta. And also there is a minus h bar square outside. Okay. Minus h bar square. Okay. So it gives you a minus h bar square, and you can see immediately dou by dou theta sin square theta gives you sin theta cos theta. There is a 2 So, it gives you minus into minus plus. So, it is 2 h bar square cos theta, the sin theta cancels off, and therefore, it is 2 h bar square y1 0. Okay. Easy. Same thing you can do for the sin theta e raised to I phi, which is y1 1. Okay. The idea of doing both of them is that because the derivative will contain both the theta part and phi part. So, if it is L square on y1 1, this is the same as minus h bar square 1 by sin theta dou by dou theta of sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square on this function sin theta e raised to I phi. So, the first term does not contain the e raised to I phi, therefore, that is unaffected, and the rest of it will give you minus h bar square 1 by sin theta dou by dou theta. Sin theta of this will give you cos theta. So, we have dou by dou theta of sin theta cos theta, and the other term will, the sin theta will cancel out. So, you will have 1 by sin theta, and the dou square by dou phi square on e to the I phi will give you minus 1 e. Right? And this is what you will get, and there is a minus h bar square also here, okay, as we decided to take it outside. We haven't done it, therefore, it is inside. So, now you can simplify this, and you will see that this gives you, when you simply cancel this out, take this derivative, this is cos theta is minus sin theta. So, it is minus sin square theta, and sin theta gives you cos square theta. So, it gives you plus cos square theta. So, that is to be multiplied by minus h bar square by sin theta, and you already have a minus h bar square by sin theta times minus 1. So, you can see that 1 minus cos square theta is sin square theta. So, you will get 2 sin theta. So, eventually, when you do the algebraic simplification, this gives you 2 h bar square sin theta e to the I phi, which is nothing other than 2 h bar square y1 1. So, L square on y1 1 gives you L into L plus 1 h bar square y1 1. So, the same thing can be verified for all the spherical harmonics which are listed all over the textbooks, and also in the Wikipedia you can find out the spherical harmonics given up to L equal to 9 and so on. In chemistry, we do not need to worry so much about L equal to 9 in the case of atomic orbitals, because L equal to 3 is the last we have, F orbitals is the most we have for the atoms. But for reaction dynamics and for microwave spectroscopy and various other places, you will need a very high value of N. Therefore, spherical harmonics are extremely important, and manipulation of spherical harmonics and the simple differential equations, integrals, all these things will give you some comfort and confidence that you can face the formal mathematical tools quite efficiently. The purpose of these tutorials is to basically tell you that there is really nothing hard. You have to just sit down and learn things the way they have to be learned, and there is no short circuiting the whole thing. You have to sit down and do the problems if you want to understand quantum mechanics. I have tried to help you as much as I can. We will continue this part of the video tutorial in the next set with the remaining 3 or 4 problems, and until I provide the solutions, the video tutorials are available on the website. I would request all of you to actually try that on your own, and then later compare your results with what I provide as solutions. Until then, thank you very much.